chapter 4, we're really going to begin to start interpreting what do those derivatives mean and how do they apply in terms of the graph. So the first section, 4.1, we're talking about maximums and minimums. So what we're saying is that on some function, there is a value that's going to be an absolute maximum, and we're going to have a value d, then there's going to be an absolute minimum. So when I plug in that number, if I get something less, I'm going to have a minimum, greater, maximum. An absolute extreme value would be the highest or the lowest. So why do we say absolute? So think of a cubic, right? A cubic has one max and one min. But what happens if we do x to the fifth? We start to get those multiple mountains and valleys. So what we're saying is there might be a local max and min, but the absolute highest point or the absolute lowest point, we're going to name absolute max, absolute min. So for instance, if I'm looking on this graph, this would be a high point, this would be a high point. We have a low point at this little valley and a low point at this little valley. But overall, this appears to be the absolute maximum because it is truly the highest point. So some examples of this are y equals x squared. This only has a minimum. It doesn't have a maximum. So because the values keep increasing, the parabola gets wider and wider, on an open interval, I don't have a max. But look over here to the right. If I limit my interval from between 0 to 2, then this point here at 2 is the highest point on the graph because I'm only looking at a little cut. So within this section, be really careful as you're working and notice if we're working on an open interval like on the left or if we're limiting the interval like we see on the right. And then we have to also be careful with are we using brackets or parentheses. So this is defined at x equals 2, making it my absolute max. This is not defined here, so then we really have trouble defining an absolute max because we talked about the concept of limit as we get closer and closer and closer to 2, but we can't include 2 there. So we just kind of have this idea of what it's approaching. So here's another graph. We don't have an absolute maximum value because it's not defined here. We do have an absolute minimum on the line as they are defined. I have an absolute minimum that is defined. I don't have an absolute maximum because it's open or not defined. So the extreme value theorem basically tells us what we already know about common sense. If something is continuous between two numbers on the graph, then it's going to have an absolute max and absolute minimum because it's defined. So there's going to be some lowest point and some highest point on the graph. So look at these. These are inclusive intervals. I have an absolute max, absolute min. Here, I don't have defined values, but I do have an absolute max because we're not including those other values. So you really got to watch and see if A and B are at closed interval or if A and B is an open interval. That's really going to make a difference. Now, when we start talking about the maxes and mins with the curves here, this would be an absolute maximum. I have a horizontal tangent, which means the slope is going to be 0 right there. Same here. This is also an absolute maximum, but as we recognize from differentiability, this is not differentiable here. So these are what we call local maximums and minimums because the absolute lowest point is over here at A. The lowest point of the graph is here. So if for some reason A was a little bit higher, maybe see right here, this would be our absolute. So our absolutes are the absolute highest and lowest point, and they have to be defined. The locals are occurring between the interval and are anywhere we have that horizontal tangent line with a slope of 0. And so that's basically the definition of what I just talked about. So looking at this, I have an absolute minimum here at P. I have an absolute maximum, it looks like here at Q. And then I have locals in all the other locations. So we're looking for things that are defined. So this is going back to the slopes of our secant lines, and what we do is as those secant lines get closer and closer and closer together, it approaches this pink tangent line, which has a horizontal line. Remember, the slope of a horizontal line is 0, so therefore the derivative equals 0. So when we are looking for our extreme given an equation, when we're not just straight out graphing, we're going to take the derivative, set the derivative equal to 0, and solve, and that's going to give us our potential max and mins. Now, a critical point is going to be more inclusive. So a critical point is going to be anywhere the derivative is 0 or where it's not differentiable. So think about an absolute value. It's not going to be differentiable at the vertex at that very corner because I have too steep of a slope. So I'd have to look at that vertex point knowing the graph of the absolute value, because there's no calculus I can use to get to knowing where that vertex is. That's my algebra background. So we're really going to have to blend what do we know about the end behavior of these graphs, what does the shape of the graph look like, with actually taking the derivative and setting it equal to 0. So here we're talking about we can have local maxes and mins where the derivative does not exist. The derivative doesn't exist anywhere it's not continuous, or at corners, cusps, oscillations that are moving too quickly, and all those things we learned back in week 2 and 3. So we have to account for both. Now, this is a really tricky place that things happen. Do you see that horizontal tangent happens for like a whole interval? So at that point, it's really hard to declare that point a maximum or a minimum because something else is going on there with it being constant for so very long. So that's something we're going to kind of be on the lookout. Same thing here. My derivative doesn't exist. I don't have that local max or a min, but it's still going to be considered a critical point. It's a point worth investigating. So if we're locating these on a closed interval, here's what you do. You are going to take the derivative, set it equal to 0, solve. You're going to identify any corners, cusps, oscillations, removables, asymptotes, any of those things. Those are all candidates for the max and the min. Then we're going to take all those critical points and plug them into the original equation. Not the derivative, the original equation. Then, once I've plugged in all my critical points, I'm also going to plug in the value for A and B. I'm going to take that list of numbers, which are my Y values that are occurring on the graph. The largest one is my max. The smallest one is my min. So when we're looking for an absolute extreme value on a closed interval, not locals, absolute, differentiate, set equal to 0. Look for where the derivative does not exist. Those are my critical points. Take all the critical points, plug them into the original, plug the endpoints into the original. The highest value is the max, the lowest value is going to be the min. So this here is an example of x to the 4th minus 2x cubed. So I would differentiate this to get 4x cubed minus 6x squared equals 0. So I'm going to factor out my x squared. I'm going to get x equals 0. And then I'm also going to factor out and solve to get my other critical point. But because I'm on an interval that's defined from -2 to +2, I'm going to plug those values in. And what I'm going to see is my maximum is actually going to be my endpoint and not my critical points. Okay? On my endpoint, not my critical points. And that is happening because I have an absolute extrema. Same thing here. We can differentiate this. We know there's a corner happening at 0 because it's to the 2/3 power. I would distribute the x to the 2/3 through the parentheses, guys, instead of trying to do a product rule there. So I would do 2x to the 2/3 minus x to the 5/3. And then I would differentiate that. Then you're going to plug in your values on the interval that is closed. So really, again, we want to be cautious with how we're finding those extrema points. So what does the derivative tell me? If the first derivative is positive, the original function is increasing. First derivative is positive, original function is increasing, because if my slope is positive, my line is going up. If the derivative is negative, the original function is decreasing because my slope is going down. So this is what this looks like. This is an increasing line. It's going up. So that means the derivative from here all the way to here is going to be positive. And then I'm decreasing, so my derivative from here all the way to here is going to be negative. And this is just an image that gives us the idea of how we know things are positive or negative based on those tangent lines. The slope of this tangent line is positive because it's headed up. The slope of that tangent line is negative. So the derivative can tell us a lot of things. So when we're testing for intervals of increasing and decreasing, let's go back to this image. Things are going to increase or decrease between two local extremas. So when I'm setting those derivatives equal to 0, I can set up an interval with each critical value, and I can plug that into my first derivative to know if the graph is going up or down. So this is kind of a nice sign chart. I would suggest screenshotting this and maybe putting it printed out somewhere. The sign of my derivative is positive. My original function is increasing. Negative, original function is decreasing. And then I'm going to look at my horizontal tangent lines. Now, it might happen that you have multiple critical values and it's increasing on both those intervals. That's fine. So don't panic if you get two intervals that are next to each other that are both increasing. That doesn't mean you did it wrong, okay? So looking at this graph, I have the first derivative would be positive between -4 to 0. It'd be negative from 0 to 4. It would be positive again from 4 to 6. And then at 6, we kind of skip over and we've got from 6 to infinity because we don't have a closed interval. So it's really easy if you just really keep that locked down in your mind with the positive and the negatives. And these are just some additional examples to work on to look at how things are happening. Now, how do I know that something is a local max or a min using this increasing and decreasing idea? Well, if a function goes from decreasing to increasing, that means I have a change in the sign of my derivative. My derivative is negative, it changes to positive. So I have a min, because that's the only way to get a minimum is if I'm decreasing then increasing. So when you're doing the first derivative test and you get your critical points, you can plug in a value to the left and to the right of each critical point, and without a graphing technology, you can know if you have a max or a min. Now, a maximum is going to occur when I'm increasing and decreasing. So the first derivative is going to be positive and negative. And when you're plugging in, when I say look to the left or the right of the critical point, just look at one value over. So if your critical point is 6, look at 5 and 7. Plug in 5 and 7 to your derivative. If you get a positive number for 5 and a negative number for 7, you have a max. That is a major takeaway here. And this graph is giving us an idea of, I have absolute max and mins on my endpoints. I have my derivative is 0 here, but see how this is a kind of a point of inflection. It takes a long time, so we don't consider that our max or a min. We have to have that nice cup feeling where things are going to pull there. So the first derivative test is exactly what I was saying to do. Take the derivative, set it equal to 0. Look at your places it's not differentiable. That whole list is your critical points. Instead of plugging into the original function, because we're not given an interval, we are going to set up the first derivative test. So this is why we're using this and not the other method. We don't have a closed interval. So you're going to take all those critical values and set up intervals on the number line. So for instance, let's say I have the following critical values: 0, 5, and 8. I would set up my number line with 0, 5, and 8. Then I would pick numbers on the left and the right. So -1, let's say 1. I'm going to plug -1 into my first derivative, not the original, the first derivative. I'm going to plug 1 in to my derivative. If I get positive negative, I have a max. If I get negative positive, I have a min. If I get positive positive, I have nothing. So it's possible that you could get a positive at -1 and a positive at 1. It just means that 0 is not going to be an extrema. Then I'm going to do the same thing over here with 5. So let's do 1 and 6. Plug it into my first derivative. Again, positive, negative, increasing, decreasing, max. Negative, positive, decreasing, increasing, min. So it's really nice when we set up these first derivative tests because I'm not having to actually graph something, and some functions are incredibly hard for us to actually get an accurate picture of on a graphing calculator, because I could have cusps, I could have asymptotes, there could be things happening outside of my graphing window. So this can be a really reliable way to look at things and to look at maximizing and minimizing related rates. So that's another common application of what we have. If I have a local extrema, that implies there's going to be a maximum extrema. This is kind of a theorem. So if something is local, that kind of means you have more than one. So logically, it's going to follow there should be an absolute. If you've got locals, there's going to be some highest or lowest point. And so here's some examples of this with our tangent lines. We have things called concave up and concave down. So this can sometimes be kind of hard to see. So concave down would be if you take your left hand and you curl your fingers. That's going to be concave down. Or if you rotate that hand and you get a parabola with a max, that's going to be concave down as well. Concave up would be taking your right hand and curving your fingers, or holding it down as a cup and having a minimum. So concavity is going to happen by our second derivative. So we're going to look at taking the second derivative, setting it equal to 0, adding that in to my numbers and to my problems. If the second derivative is positive, it's concave up. If it's negative, it's concave down. So why is this important? Because when I'm drawing a graph, I have to know what the concavity is in order to sketch it. Because look at this. That's increasing, but so is this. Do y'all see these are both increasing functions? But the concavity is different. So how the graph looks could be radically different if you didn't consider the second derivative. So this is why we're going to plug that value in from the number line we had into our first derivative to see if it's increasing or decreasing. Plug that same number into our second derivative to find out if it's concave up or concave down, so we can actually draw the graph. Now, if we go from positive to negative or negative to positive, we have a point of inflection. So what a point of inflection tells us is that we have a potential maximum or minimum happening. Potential. It doesn't have to be one, but it's potential. Because notice here, my concavity changes here, but this isn't a max or a min. This is a point of inflection. Here, I have not an inflection point because my concavity doesn't change. So it's not necessarily implying a max or min. It's implying when I have that change in concavity that's going to occur with what's happening there. Here's another example where the concavity is changing or not changing, and the graph can be doing very different things there. So this is what increasing concave up looks like, increasing concave down, just exactly what I was drawing before. So what I would advise you to do is go ahead and make a quick sketch of this so you can refer back to it all week, because sometimes the visual side of this just doesn't click with us, and we have some issues trying to sketch out those graphs fully. Now, my second derivative test, I can basically bypass the first derivative if my second derivative goes from being positive to negative. Then I can potentially have a max or min happening. Or if my second derivative is, positive, that would be a min, because the only way to get that to happen would be an empty cup. When I say empty cup, let me show you what that means. That means this. So what this means is I can take the second derivative, I can skip completely plugging into the first derivative and just plug it straight into the second derivative to see what kind of max or min that I have. If I plug it in the second derivative and it's negative, then it's going to have the maximum. So the second derivative test is bypassing the first derivative process where you're setting up the interval and you're plugging in multiple numbers. Why would we use the second derivative test? Well, it's better to do half the work, right guys? So if I plug in the number one time in the second derivative, I'm saving a ton of time with not having to plug in two numbers and look at what's happening. But as I note, if you get 0, it's going to be inconclusive. So here's an example of if I have the first derivative, it equals 0 at c, and then I plug c into my second derivative and it's positive, I got a local minimum. The derivative is c is 0, I plug it into the second derivative, I get a negative number, it's a maximum. And that concludes what we're looking at for this section. So here's a quick chart to quick reference what to draw. So you may want to quickly screenshot this and print it out so you can make sure that you're following along with how to sketch these curves within the lab, and knowing when things are increasing or decreasing. But sometimes it can just be hard to visually organize all of that information.